Good afternoon, everyone. So, I am Ankara Karthika, a research scholar from IIT Hyderabad. So, I am handling the problem solving sessions for the NPTEL course Fluidization Engineering. The course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati. So, the problem solving sessions are happening every Saturday from 3 p.m. to 5 p.m. Unless informed of some other times, these sessions will be going in the same time. So the time now was 3:02, I guess. So let us wait for 2 more minutes for others to join. So we can start the session by 3:05. In the meantime, if you have any doubts from the last session, you can ask. So yeah, we'll see the session. In between, if you have any doubts, you can always ask. Okay. So if in case there is a power cut, please stay on the call. The call is available for everyone to join. Like it is not like it will be done only after I come or something. So I request every one of you to be in the call for me to come back. I'll be joining back in 3-4 minutes max, because I am working from Wi-Fi. So if power cut happens, I'll cut the call and then join back through my mobile data. So that's it for my end. And if there are any doubts, you can ask during the session as well as at the end of the session, anything which is convenient for you guys. And I also request you people to submit your feedbacks for the session in the NPTEL website, which for which they send mail sometimes. So that would be helpful. And apart from that, if you have any direct suggestions for me, you can say during the class as well. So that's it for from my end. So what is the time now? Time is 3:04. So yeah, we will start with the session. Like we'll go through introduction, and then if anyone is willing to join, then let them join. For them, the sessions are available through recorded videos as well. So it would be helpful for them if they see those videos later also. So that would not be an issue. So yeah, fluidization engineering, as you all know, it might not be a direct core course for most of the people from chemical engineering background. It might be your elective, or you would be registered for the course because of the project details. Like if your project is related to that, you would be in that. So I would like to start by giving you an introduction on what is fluidization. So fluidization is nothing but it is the process in which we pass the fluid inside the bed at a very high velocity, like we can say sufficiently high velocity, so that the particles will also start to move. So since the particles are behaving like a fluid, we call it fluidization. And this has several advantages in terms of having more solid fluid contact than the packed bed. In packed bed, if you imagine, the solids are packed inside a certain region, and when we pass the fluid, the surface area of the solids coming in contact with the fluid is kind of limited when we compare it with the fluidized bed. So in terms of heat transfer and mass transfer, this fluidization has several advantages compared to packed bed. So that doesn't mean it has only advantages and no disadvantages are there. There are certain disadvantages in fluidization as well, in terms of erosion of particles. Those things are there. and which would offer a kind of disturbances. So depending on what our requirement is and how much we are willing to put in that particular system, we can go with packed bed or fluidized bed depending on the requirement. And also it also depends on the pumping cost of the fluid. So those things are only we are going to deal with in today's problems. It is related to distribution system, that is the fluid distribution system. So let us go on. And so the course layout, as you all know very well by now, it is a 12 weeks course. So in the weeks before, we have seen the introduction to fluidization and advantages and disadvantages of using fluidized beds and industrial applications. Also, we have seen about the characteristics of solids and how we classify the solids into four categories: gelate A, B, C, and D, and how different solids behave differently inside the fluidized beds at different velocities and depending on the fluid medium as well. So, and last week it was about flow pattern of fluidization system, especially about the pressure drop and its models to analyze. In today's class, we'll be dealing more with gas distribution system and similar problems from that. And yeah, hereafter it is not exactly followed with this, but in today's class itself, in week 5 the syllabus has covered type of gas distributors in small and large scale fluidized beds and design of those distributors. And later on, from next week's or the week later, we'll be discussing about bubbling fluidized beds, gas dispersion and gas interchange in bubbling beds, and so on, like entrainment, elucidation from fluidized beds, in which the solid particles will start to escape from the bed. And week 9 it is about attrition. As I told, it is the mechanism in which the solid particles rub against each other, and because of that, loss of material may take place. And last few weeks it would be about mass transfer and heat transfer phenomena happening inside the fluidized beds. And that's it, like we'll deal with those as time comes. So in today's problem, we are going to see about sample problems from week 5 and also assignment problems from week 4, for which submission deadline has crossed. So the sample problems from week 5 will help you solve assignment problems. So you can do them and submit it before Wednesday. I think Wednesday is the deadline. Kindly check it. But to my knowledge, it is on Wednesday. But it would be helpful for you guys to solve similar problems so that you will have an idea. So now moving on, for reference books. Reference and books we have Cooney and Levenspil's Fluidization Engineering, and Gidaspo's Multiphase Flow and Fluidization, Continuum and Kinetic Theory Description, and Gibbelaro's Fluidization Dynamics, and S.K. Majumder's Hydrodynamics and Transport Processes of Inverse Bubbly Flows. So out of all these books, the Cooney and Levenspil's Fluidization Engineering covers all the aspects related to fluidization. So if you have at least read the book once, if you are thinking of majoring something in fluidization, it will be very helpful. So now let us move on to the problems. So this is, before moving on, we will have an introduction to gas distribution system. So gas distribution system, it is that we have distributors, which for small scale industries we use certain types, and for large scale industries, in small scale studies we use certain types, and large scale studies we use different one. Why that is the case? Because in small scale studies in fluidization, we use ceramic or sintered metal porous plate distributors. For example, in academic labs and all, we'll be using ceramic or sintered metal porous plate distributors because they give uniform gas distribution at a high flow resistance. We can also use filter cloth, compressed fibers, and compacted wire plate or thin bed of small particles. For example, we'll be having some wired mesh, wired plate or something, and we'll be putting that and to act as the distributor plate, and these things can be used in small scale studies. Some of these materials should be reinforced by sandwiching between metal or wire plates with large openings. Um, Imagine your gas distributor only holds the entire weight of these solids, so it should be able to withstand the solid weight also. In that case, if you are placing a thin layer of wired mesh or wired plate, it would not be able to support it, the material, when we are passing air or at a normal condition also. Sometimes we need to put those wired mesh or something between two metal plates or wired plates with larger openings, so that we can offer the same gas flow by sandwiching that particular thing in between a metal or wired plates. So these are the cases how we use distributors inside in the small scale studies in fluidization, in while doing studies in labs, everything. But if we are going to use those things in industries, they have several drawbacks. The same thing which we use in laboratory scale studies cannot be used in industrial operations. Why? Because they have certain drawbacks like high pressure drop, leading to increased pumping power requirements. Because imagine if these things offer higher pressure drop, we need to increase the pumping requirements, and if we are increasing the power pumping requirements, the electricity cost associated with that will also be increased. So in that case, the cost is a cost plays a major role. So that is one thing. And second one is low construction strength. And these materials will be of a low construction strength and we cannot use it in a large scale purpose. Imagine in industries everything will be so huge in capacity. We cannot use these materials because they would be of a less strength, and also like high cost for some materials. Some materials, since it is in laboratory scale, we can use them at a smaller size, but imagine in the industrial scale we cannot use those materials because it would be very costly to go with those materials in such large size, and also they might also require maintenance or replacement in the future, which again adds to the cost. So high cost for some materials and low resistivity against thermal stresses, again this is the case, and possible gradual clogging by fine particles or products of corrosion. Like as we have seen, the particles into the fluidized beds, when we pass the fluid, they start to moving, and when they move, they might rub against each other and the particles might break, and because of that finer size particles might be produced. That is one thing. Or the particles that we are using in the study itself might be finer sized, and some corrosion error, things might happen, and finer size particles or something will be produced in addition to the materials being used inside the system. So those particles might be clogging the fine pores. Imagine fine pores getting clogged. We cannot offer the same gas flow resistance or same gas flow pattern of what we offered in the small scale bed to the large scale systems, because the bed now is clogged by fine particles. So these are the things of how we are using different materials for the small scale studies and the high industrial scale studies. So just to give you an idea, because some of the questions from this week is completely based on these things, so I want to give an idea of how things are going, so that we can answer the questions directly when they are presented. So the first question, now let us move on to questions. The question one, it is the disadvantages of industrial scale distributor for small scale fluidization is. So as we have now seen that, what are all the disadvantages we will be facing when we use the same material for which we have used in small scale distributor to the larger scale distributor. That is what disadvantages we will be facing when we are using small scale systems distributor in the larger scale systems. So the first one is increased pumping power. Yeah, this one we have seen how it is affecting the increased pumping power, because small scale fluidization distributors will be offering higher pressure drop and because of the higher pressure drop we need to increase the pumping power. So first one is true. Second one, it is high construction strength. And third one, it is high resistivity against thermal strength and clogging due to large particles. So the option B is that high construction strength. That is not true. Those materials are offering us low construction strength. So that is why we cannot use these materials in large scale systems. And third one, it is high resistivity against thermal stresses. Again, they are offering very low resistivity against thermal stresses. That is the reason we are not going with that. And last is clogging due to large particles. Again, this is false because what is the reason? Clogging happens due to spinal size particles. Clogging does not happen due to larger size particles. So option A is the right answer. Let us now look at the answer. Option A, increased pumping power. Rest all are contradictory. Like it is offering lower construction strength and it is offering low resistivity against thermal stresses, and clogging happens due to smaller size particles. So that is for question 1. Just a minute. I don't know why, but my mouse is not moving beyond. Mm, why this one is. Insert slide number. Okay. Oh, I hope it is sorted now. Now let us go to question 2. In question 2, it is asked that a curved plate distributor is used for. So there are various types of distributor like porous plate distributor, perforated plate distributor, curved type distributor, curved plate distributor, and tubes and bubble cap. All those things are there. So why we go for curved plate gas distributor? It is option A, withstanding less load. Option B, for high thermal stress. Option C, low temperature operations. And option D, none of the above. So answer is option B, I guess. Yeah, for high thermal stress. Why we go for curved plate distributor? Curved plate distributor is used for high thermal stress operations and it can withstand heavy load and high thermal stresses. So that is the answer. See, in exam the same question might be asked but different options would be twisted. So you must be prepared to answer anything, and questions can be asked from any way. So you should also be probably knowing why option A is wrong. Option A is wrong because it is mentioned that it is withstanding less load. But in reality, curved plate gas distributor is used for withstanding high load and high thermal stresses. See, the distributor is like this curved end, right? The construction of those curved plate gas distributor is very tough, and if we are going with that high that difficult distributor design, it should be having a certain advantages. So what is that? Withstanding less load doesn't make sense at all, because it should be able to withstand high load in that condition. Then only we can go with curved plate distributors. Otherwise, there is no need to go for that as well. And second one is high thermal stress. So again, like it needs to be withstanding high thermal stress. So and low temperature operation, again there is no need for having such design to deal with low temperature operations. So that's it, and we'll go to question 3. Hmm. Question 3. Now it is asked the type of distributor plate which can be used for high temperature operation. Option A, it is perforated plate distributor. Option B, bubble cap distributor. Option C, Tuer distributor. Option D, Sparger distributor. So high temperature operations, this type of distributor plate uses, I think, Tuer distributor. Option C, Tuer distributor is the right answer, because if you remember TUS, it is used for high temperature operations and it is used in highly reactive environment. So that is why we go for TUS distributor when we are dealing with high temperature and highly reactive environment. So that is question 3. Now we'll go to question 4. In question 4, the main advantages of bubble cap distributor are: option A, minimize weeping; option B, lower pressure drop; option C, good turn down ratio; option D, all of this. So in this question it is asked about the advantages of bubble cap distributor, and so the options given are minimizing weeping, it lowers pressure drop, and good turn down ratio. So according to bubble cap distributor, if you look at it, it offers minimized weeping, that is why we use that. And second one, it is lower pressure drop. The bubble cap distributor design is quite difficult than a perforated or porous plate distributors. So in that case, it should be offering some quite good advantages. So those are like it minimizes weeping and it offers lower pressure drop and it costs a good turn down ratio. If it is lower pressure drop, pumping cost would be reduced. So that is for this question. So answer is all of these is the right answer. 5. The dead zone shrinks with decreasing particle size. Option B, increasing gas velocity. Option C, decreasing orifice size. Option D, increasing spacing of orifice. So answer is increasing gas velocity, because dead zone is nothing but where the particles are settling down and it is impossible for those particles to move and circulate. So in that particular case, um, we need to be focusing on shrinking that particular area, because if the solids in that zone is inaccessible, they will not be used in reaction or any heat transfer or mass transfer operations. Those particles would not be participating. So our ultimate aim is to shrink the dead zone, and for that, what is the thing it can be done? Option A, it is decreasing particle size. Yeah, this is true. This is false, because dead zone shrinks with increasing particle size. And second one, increasing gas velocity. This one is true, because when we increase the gas velocity, the particles will be forced to move. And since they are forced to move and come back, and the circulation is fast, the dead zone also shrinks. Option C, it is decreasing orifice size. Again, this is false. We can increase the orifice size to decrease the dead zone, but in decreasing the orifice size does not allow it to happen. And last, again, it is increasing spacing of orifice. If we increase the spacing of orifice, imagine one orifice will be in one corner and the second orifice will be in some distance away from the first one. So the air flow rate, or the fluid inlet is at two different points, and in between they have some space, and if we are increasing the spacing of the orifice or decreasing the orifice size, that particular space is getting increased. So in that particular zone, the fluid is kind of inaccessible to the solids. So dead zone forms and over there. So option B is the right answer. as it is rightly given, option B is the right answer. Increasing gas velocity. Dead zone shrinks with increasing gas velocity, and it can also be done by increasing the particle size, opposite of option A, and increasing gas velocity, option B is true. And option C, it is decreasing orifice size. Decreasing orifice size, imagine again the distance between the orifice increases, and therefore the particles would be reaching the dead zone. And so on the other hand, if we are increasing the orifice size, we are able to minimize that particular zone, and also decreasing the spacing of orifice also decrease the dead zone. So let us move on to question 6. Question 6, it is asked that with an increase in the liquid jet velocity, penetration length Lj dash. Option A increases, option B decreases, option C remains constant, option D infinite. So I would like any one of you to give me an answer for this question with why. With an increase in liquid jet velocity, the penetration length is nothing but how far the bubble travels, or the bubble size reaches in the shape of a jet before it gets detached from the orifice. That is known as jet penetration length, or known as LJ. So if we are increasing the liquid jet velocity, what happens to penetration length? Penetration length actually decreases, because if we are increasing the velocity, the movement of solids is also there. So the bubbles get detached from the orifice, and therefore the size of the bubbles decreases. So with an increase in liquid jet velocity, the penetration length actually decreases, because the particles also starts to move, and the chances of the bubble getting detached from the surface of the orifice is there, and also lateral movement of solids will be taking place with increase in the liquid jet velocity. So now let us go to question 7. Question 7, with an increase in the orifice flow rate, bubble size dash. With an increase in orifice flow rate, bubble size dash. Option A constant, option B decreases, option C increases, option C D both B and C. I think option C is the answer. Increases. With an increase in orifice flow rate, imagine the bubbles will be growing in size, and therefore the bubble size increases. Orifice flow rate is nothing but the flow rate at which the air is, or the fluid is passing through the air, through the gas distributor in coming in contact with the solids. So with an increase in the orifice flow rate, bubble size increases. So option C is the right answer. Now let us go to question 8. Above single orifice plate dash. Above single orifice plate dash, jet elongates. Option B, larger bubble form with increasing orifice flow. Option C, bubble rise velocity exceeds the linear growth rate. Option D, all of the above. So I'll read the question again, and you can see the answer. Above single orifice plate dash. What happens above single orifice plate? Option A, jet elongates. Option B, larger bubble forms with an increasing orifice flow. Option C, bubble rise velocity exceeds the linear growth rate. Answer is option D, all of these. Because with an increasing in the orifice flow, the first thing to happen is it jet elongates, and larger bubbles forms with increasing orifice flow. Like if you're increasing the velocity, imagine the jet will be elongating, and larger bubble form, like jet elongation will be there. This is with above single orifice plate. And if we are increasing the orifice flow, the bubble size will be growing larger till a certain point, after which it may get broken. And option C, it is bubble rise velocity exceeds the linear growth rate, before which it would be like linearly proportional of the velocity and the bubble size. But now the bubble rise velocity, not bubble size, bubble rise velocity, the speed at which the bubbles are moving, bubble rise velocity exceeds the linear growth rate. So that is also true. So answer is option D, all of these, because three statements given are correct. Option D is the right answer. Now let us go to question 9. In question 9, it is asked that at a nozzle tube, which one of the following is appropriate? When we are using nozzle tube, which one of the following is appropriate? Option A, bubbles form and detach in random procession. Option B, poor mixing quality result. Option C, are favored if dense zones are to be eliminated on the distributor plate. Option D, at low jet velocities, bubbles coalesce into horizontal jets. So what is answer to the question? What happens when we are using tube type nozzles? At a nozzle tube, which one of the following is appropriate? So out of the four statements, we need to identify which one is the correct statement. So the first one is bubbles form and detach in random procession. That we cannot say. The bubbles will be growing from the sides of the tube, and as they grow and rise above the tubes, they grow in size. So bubbles form and detach in random procession is not true. It is not getting done in random procession. And option B, it is poor mixing quality result. We cannot say that always. So poor mixing quality is not true. And option C, it is are favored if dead zones are to be eliminated on the distributor plate. This one is true, because we are favoring the dead zones. We are not favoring the dead zones, and we are making some provision to eliminate those dead zones. By doing what? By shifting to pure nozzles. So option C is the right answer. And option D, it is at low jet velocities, bubbles coalesce into horizontal jets. Horizontal jets are the ones which have the dimensions in the how to say direction perpendicular to the fluid flow. Um, so at that point, at low jet velocities, bubbles won't be coalescing into horizontal jets. At higher velocity, things would be different, but at low velocities, the bubbles coalesce and form horizontal jets is a false statement. So answer to this particular question is question 9. It is answer is option C. At a nozzle tube, which one of the following is appropriate? Option C, are favored if dead zones are to be eliminated on the distributor plate is the right answer. Option C is the right answer. Now let us go to question 10. At a bubble cap tube, which one of the following is correct? Option A, at high gas flow rate, bubbles form with jet. Allow solids from falling through the distributor. Bubble form at bubble cap. All of these. So bubble cap tube we use. Why do we use? It has certain things. So here are few statements given in regards to bubble cap tube. We need to identify which one is the right statement. So first one is at a higher gas flow rate, bubble forms with jet. And second one, allows solid from falling through the distributor. And third one, bubbles form at bubble cap. So I think all three. Okay. Third one is the right. Okay. So bubble cap distributor at a higher gas flow rates, bubbles will form, but jet would not be formed when we are using bubble cap tube. That is the thing. So bubbles form at bubble cap. At a higher gas flow rate, bubbles form without jet. So that is the wrong thing we identified from question 10, option A. So first statement is false. Second statement allows solids from falling through the distributor. Again, this is false. Option C, bubbles form at bubble cap is the right answer. Option C is the right answer. Now let us go to question 11. In question 11, it is asked that which for horizontal jet, rate of jet penetration length for the large hole is dash. For horizontal jet, range of jet penetration length for the large hole is dash. So we need to identify a few things. First one is horizontal jet. It is given in the question that it is horizontal jet, and range of jet penetration length for a large hole is dash. So the range of jet penetration length, that is LJ, for the large hole is dash. So options, let us look at. LJ is equal to zero point 0.4 to zero point 0.7 centimeter, and option B, it is 0.1 to 0.15 meter. Option C, it is 0.5 to 0.6 meter. Option D, it is 0.3 to 0.6 meter. So we look at the options. Answer is option C, that is 0.5 to 0.6 meter. When we are dealing with horizontal jet, the range of jet penetration length for length scale is dash. The range of the jet penetration length for the length scale is dash. So it is 0.5 to 0.6 meter, 0.5 to 0.6 meter. For horizontal jet, the range of jet penetration length for a large hole is dash. So here we need to identify, not identify, we need to know three things. The first one, it is given horizontal jet. Second one is we are asked to find the range of jet penetration length. And third one is we have used the larger hole. So answer is 0.5 to 0.6 meter. If it is a smaller holes, many small holes, few large holes or many small holes, the options are varying. So for many small holes, we are going with 0.1 to 0.15 meter. That is the range of jet penetration length. What is the range of jet penetration length? It is 0.5 to 0.6 meter, and that is the range for jet penetration length. So that's it for question 11. In question 12, it is asked that the thumb rule for pressure drop across the distributor delta PD is dash. Thumb rule for pressure drop across the distributor delta PD is dash. So the options are where delta PD and delta PB are the pressure drop across the distributor and pressure drop across the bed respectively. Now let us go to question. Thumb rule for pressure drop across the distributor is dash, and in the options given, delta PD refers to pressure drop across the distributor and delta PB refers to pressure drop across the bed. So when we are clear with that, we'll go to the options. Option A, it is delta PD is equal to 0.2 to 0.7 delta PB. Option B, it is delta PD is equal to 0.2 to 0.4 delta PB. Option C, it is 0.5 to 1.0 delta PB is delta PD, and option D, it is delta PD is equal to 1.0 minus 2.0 into delta PB. So answer is option B is the right answer. Pressure drop across the distributor should be below 20 to 40% of the pressure drop across the bed. So it is delta PD is equal to 0.2 to 0.4 delta PB. I hope question 12 is clear. Question 13, it is that For a perforated and pure distributor, the distribution pressure is related to the final fluid velocity as dash. For thumb rule for pressure drop is delta PD is equal to zero point 0.2 to zero point 0.4 delta PB, that is pressure drop across the distributor should be 20 to 40% of the pressure drop across the bed. Now let us go on to question 13. For perforated and pure distribution, the distributor pressure is related to the fluid velocity as dash, where delta PD and U are the pressure drop across distributor and the velocity of fluid respectively. So, perforated and pure distributor, the distributor pressure is related to fluid velocity delta P and U. How it is related, we are going to find. So let us look at the options. Option A, it is delta PD is proportional to U power minus 2, and option B, delta PD is proportional to U cube. Option C, delta PD is proportional to U square. Option D, it is delta PD is directly proportional to U. So the right answer is option C, delta PD is directly proportional to U square is the right answer. For porous plate distributor, okay, there are two relations. The first one is delta PD is related to fluid velocity. How it is related? When it is a case with porous plate distributor. For porous plate distributor, delta PD is directly proportional to U, and for perforated and pure distributor, that is what is asked in our question. So perforated and pure distributor, it is delta PD is proportional to U square. Whereas in the porous plate distributor, if it is asked for porous plate distributor in the question, please be conscious enough to put U. Delta PD is proportional to U. For perforated and pure distributor only, delta PD is proportional to U square. So for this question, the answer is C, that is delta PD is proportional to U square. That's it for question 13. And let us go on to question 14. Question 14. The stirring effect of the distributor is defined as where alpha is the stirring effect distributor and rho g and UOR is the density of gas and the orifice gas velocity. Delta PB is the pressure drop across bed. So, wait. Question 14. It is stirring effect of the distributor is defined as dash. In that particular equation, we need to find, in that equation, alpha is the stirring effect of the distributor and rho g is the density of gas and UOR is the orifice gas velocity and delta PB is the pressure drop across the bed. So that's it. Now we will see the answer. Alpha is equal to rho g UOR square by 2 divided by delta PB, and option C, B, it is alpha is equal to rho g UOR square divided by 4 divided by delta PB. Option C, it is alpha is equal to rho g UOR divided by 2 divided by delta PB. Option D, it is rho g UOR cube divided by 2 divided by delta PB. So that is the options. I'll tell you the term that comes in the equation is a kinetic energy term. So how do we write? Half rho v square or half mv square. M is here nothing but rho, whatever it is, but it is kinetic energy to the pressure drop. So stirring effect of the distributor is defined as the ratio of C something kinetic energy to the distributor pressure drop, sorry, bed pressure drop. So on that basis, it is kinetic energy is half mv square, so it is half rho g, that is rho g into v square. V square here is the orifice gas velocity UOR square by 2 divided by delta PB. So option A is the right answer. So answer is option A. Alpha is equal to rho g UOR square divided by 2 divided by delta PB. Kinetic energy of the orifice jet, that is what I meant here, that is half rho v square. Kinetic energy of the orifice jet divided by resistance of the bed. Resistance of the bed is given in terms of pressure drop. So answer is option A. Now let us go to question 15. The jet will punch right through the bed causing severe gas passing when dash, where alpha is the stirring effect of the distributor. So what is asked in the question? In question it is asked that jet will punch right through the bed causing severe gas passing when, and alpha is the stirring effect distributor. Alpha is the stirring effect distributor. So if we look at the options, it is alpha is equal to 1. Option B, alpha is greater than or equal to 1. Option C, alpha is greater than 1. Option D, alpha is less than or equal to 1. So jet will punch right through the bed causing severe gas passing when alpha is dash. So this alpha is nothing but stirring effect distributor, and it is given by half rho v square divided by uh, delta pb, that is the resistance offered by the bed. So if jet will punch right through the bed, it means that it is passing with a higher it is coming with a higher velocity. So alpha is equal to rho g uor square by 2 divided by uh, not divided by delta pb. So I mean alpha is equal to half rho g uor square divided by delta pb. So answer is option C. Alpha is greater than 1. When the air is, fluid is velocity is high, so it will cause the kinetic energy will also be very high. So in that cases, alpha it will punch right through the bed. So answer is option C. Alpha greater than 1. So when alpha is less than or equal to 1, jets will not cause much to the bed stirring and bubble rising. So when alpha is less than or equal to 1, these jets will not be causing any much difference to the bed stirring or the bubble rising. But if the alpha is greater than 1, at that condition we can say that it is coming with a high velocity, and the resistance offered by pressure drop of the bed is also very low, because that term comes in the distributor. So that is again low. So it is alpha is on the whole is very high. So alpha is high, jet will punch right through the bed. On the other hand, if alpha is low, there is high resistance offered by the bed, and also the velocity of UOR is very low. So jets will not cause much to bed stirring and bubble rising. So even if it is same, that is what it means by alpha is less than or equal to 1. Some case it is like kinetic energy is equal to pressure drop of the bed. So even in those cases, it will not cause much to bed stirring and bubble rising. So that is question 15. Now we'll go to question 16. In question 16, effect of excess distributor pressure drop depends on. Question 16, it is giving that effect of excess pressure distributor depends on dash. Option A, it is power consumption for the blow air. Option B, it is total pressure drop. Option C, it is the construction cost of compressor increase. So the question is effect of excess pressure distributor pressure drop depends on all of these. So when the pressure distributor pressure drop is high, what would be the effects that is being observed? So first one is power consumption for the blower. Yes, it affects the power consumption for the blower. And total pressure drop, because the if the distributed pressure drop is high, again it will affect the total bed pressure drop. And construction cost of compressor will increase. Again, if pressure drop is high, you need to pass it at a very high speed. So again, construction cost of compressor increase and power consumption increase. So all of these is the right answer. So all of these is the right answer. Now let us go to question 17. Question 17 is a problem. Okay. How many problems do we have? Okay. Okay, we'll see this problem and take a 5 minutes break, and then we'll come back and continue the session. In question 17, what is asked? A fluidized bed reactor for the production of polyethylene is attached to a compressor to transport the reacting fluid to the bed in the presence of a catalyst. Calculate the ideal power consumption for bed operation. The inlet pressure and temperature for the gas entering the compressor are 101 kilopascal and 20 degrees Celsius respectively. Required data are delta P grid is 6 kilopascal and delta P bed is 15 kilopascal, and delta P cyclone plus filters is 12 kilopascal and delta P exit is equal to 350 kilopascal, and flow rate Q is 10 meter cube per second, and use eta is equal to 0.85, gamma is equal to 1.4. Delta P grid is the pressure grid distributor. Delta P cyclone plus filter is the cyclone and pressure filter. Delta P exit is the exit pressure. Q is the flow rate, eta is the efficiency, and gamma is the ratio of specific heat of gas. So what is being asked in this question is that we need to calculate the ideal power consumption for bed operation. So we need to know what is the ideal power consumption for the bed operation. So for that, in the question it is given that a fluidized bed for the production of polyethylene, it is attached to the compressor. So we are producing polyethylene by using fluidization operation as one of the things in the whole setup, and it is attached to a compressor. So obviously if you are passing the gas, you need a compressor because you will be passing it at a higher velocity. Is attached to a compressor to transport the reacting fluid to the bed. So we are passing the reacting fluid to the bed, that is the air or something. We are passing it to the bed by using compressor, and we need to calculate the ideal power consumption for the bed operation. So inlet pressure and temperature is 101 kilopascal and 20 degrees Celsius, normal conditions, standard condition. And the data given is pressure grid distributor and bed pressure drop and cyclone plus filter pressure drop and exit pressure, and the flow rate of the fluid is 10 meter cube per second, and we are given the efficiency is 85% and ratio of specific heat of gas, that is Cp by Cv, is 1.4. So we'll see what and how to do this problem. Before that, let us check the options. Option A, WS ideal is 1432 kilowatt. Option B, WS ideal is 1624 kilowatt. Option C, WS ideal is 1638 kilowatt. Option D, WS ideal is equal to 1737 kilowatt. So answer for this particular question is option C, I guess, C, 1638 kilowatt. So now let us see how to solve this particular problem. So for that, first we need to identify what is given in the question. So for that, given pressure is given 101 kilopascal, that is inlet pressure is given, inlet temperature is given 20 degrees Celsius, and grid pressure drop is given as 6 kilopascal, and bed pressure drop is 15 kilopascal, and cyclone plus filter pressure is 12 kilopascal, and exit pressure is 350 kilopascal, and Q is 10 meter cube per second, and efficiency is 0.85, gamma is 1.4 kilopascal. For that, what are we asked to find? We are asked to find the WS ideal. And what is the formula we need to use? We need to use this particular formula for calculating the WS ideal, that is the power consumption. So WS ideal is given by gamma minus 1, P1 V1 into P2 by P1 to the whole power of gamma minus 1 by gamma minus 1. The whole thing is the power consumption formula. So now we will substitute all the known values in this particular formula. So we know gamma is 1.4, P1 is 101 kilopascal, so 101 into 10 power 3, V1 is 10, it is in meter cube per second, and it is P2 by P1, P1 is 101 kilopascal to the power of 1.4 minus 1 divided by 1.4 minus 1. So what is missing in this formula is that we need to know what is P2. So how to identify what is P2? So P2 is given, okay, let us again see, these are the given things. So now we need to identify P2 first. So P2 is equal to exit pressure. For the whole bed operation, what is the exit pressure? It is like all the pressure drops, like grid, bed and cyclone filters and the exit. If we add, we'll get the P2. So it is 6 plus 15 plus 12 plus 350. It gives us 383 kilopascal. So now we know P2. So we are going back to the formula and substituting the values in the formula again. So W is ideal is equal to 1.4 divided by 1.4 minus 1 into 101 into 10 power 3 into 10, that is V1 into 383, P2 by P1, 383 kilopascal by 101 kilopascal to the whole power of 1.4 minus 1 divided by 1.4 minus 1. So substituting gives us 1638.48 kilopascal. Like unit would be 3000 will be coming. So if you take that, it will give us the unit in kilowatt. So that is how we solve this particular problem. So if we go back to the question, it is we are asked to find the ideal power consumption for the bed operation, and for that given data is all these things. For that we need to, how will we go about calculating? First we have written the given and we need to find the PWS ideal power consumption, and so the formula is this: WS ideal is equal to gamma by gamma minus 1 into P1 into V1 into P2 minus P1 the whole power gamma minus 1 by gamma minus 1. So in this we know everything. Gamma is 1.4, P1 is 101 kilopascal, V1 is 10 meter cube per second, and P2 is unknown, P1 is 101, and gamma minus 1 by gamma minus 1. So now first we need to identify what is P2. So for that reason we are going to this. P1 is 101 kilopascal, P2 is unknown. So we are adding all the pressure drops, that is grid pressure drop, bed pressure drop, cyclone plus filter and the exit pressure drop. So now we are able to add all these and we are getting the P2 as 6 plus 15 plus 12 plus 350, it is 383. 12 plus 6, 383, and we are substituting 383 in this formula, and we are getting the final answer as 1638.48 kilowatts. So be careful with the unit and maintain consistency. So for this particular question the answer is kilowatt. and I mean the options are given in kilowatt. So that is one thing, and that is how we solve this problem. So if you have any doubts, you can ask. So yeah, that's it for question 17. Now, before moving to question 18, let us take a 5 minutes break. On the time now is 4:1. I mean 4:2. So we'll meet again by 4:6. Thank you. So yeah, we'll see. Sorry, it got delayed. But okay, let us start with question 18. In question 18, it is asked that a gas stream was compressed by an adiabatic reversible compressor from pressure 1 atmosphere to final pressure 10 atmosphere at room temperature 20 degrees Celsius through a fluid bed system. Okay. A gas stream is compressed by an adiabatic reversible compressor from pressure 1 atmosphere to 10 atmosphere at room temperature 20 degrees Celsius through a fluid bed system. What is the outlet temperature given the ratio of specific heats as 1.33? So what is being asked? We are compressing the air gas stream from 1 atmosphere to 10 atmosphere at a room temperature of 20 degrees Celsius through a fluid bed system. So what is the outlet temperature? If the ratio of specific heats, that is gamma, is 1.33. So we'll look at the options. Answer is option A 518.78 Kelvin, option B 456.32 Kelvin, option C 308.56 Kelvin, and option D it is 263.47 Kelvin. I think option A is the right answer. How will we do that? Here we are using adiabatic reversible compressor from to compress the gas from 1 atmosphere to 10 atmosphere. So initially the temperature is 20 degrees Celsius and gamma is given as 1.33. So if T1 is 20 degrees Celsius, in kelvins it is 293 Kelvin. We'll see this is solution. So first, as always, we'll write the given things. P0 is 1 atmosphere and T1 is 10 atmosphere and T0 is 20 degrees Celsius or 293 Kelvin and gamma is 1.33. So after that we need to find T1 outlet temperature. So formula is T1 by T0 is equal to P1 by P0 gamma minus 1 by gamma. So T1 by T0 is equal to P1 by P0 gamma minus 1 by gamma. So we are checking that, substituting everything we have known, and we are getting T1 is equal to T0 into P1 by P0 gamma minus 1 by gamma. 1.33 minus 1 divided by 1.33. So what is the answer we are getting? I'll check once again. 1.33. 10 power this 1 power 1.33 minus 1.33. So if I take 1, what is 0.1? Okay, so we are getting the answer as 518.78 Kelvin. T1 is equal to T0 into P1 by P0. P1 is 10, P0 is 1. So both are in atmosphere. So 10 by 1 power gamma minus 1 by gamma. So gamma is 1.33, gamma minus 1 by gamma gives us 518.78 Kelvin. So that is how we do this, and therefore the answer is option A. If you go back and check, answer is option A 518.78 Kelvin. So that is one. Now let us go to question 19. In question 19 it is asked that the ratio of specific heats of gas is CPG, CVG, is dash. So where CPG and CVG are specific heat capacity of gas at constant pressure and volume respectively. So CPG is the constant pressure, specific heat capacity of gas at constant pressure, and CVG is the specific heat capacity of gas at constant volume. And what is the ratio of specific heat of gas? So it is gamma is equal to Cp by Cv. So let us look at the options once. Option A, Cpg by Cvg. Option B, Ctg by Cvg. Ctg is nothing but specific heat capacity of gas at constant temperature. And option C, it is Cpg by Cv. And option D, it is Cg by Cvg. So answer is option A, Cpg by Cvg is the right answer. That is question 19. Then let us go to question 20. In question 20, in actual operation, a two-stage compressor with frictional losses satisfies which one of the following? Ws actual and Ws ideal are the actual shaft work and ideal shaft work respectively. So in actual operation, a two-stage compressor is working with the frictional losses that satisfies what? Which of the following it satisfies? And options are given. Before looking at the options, we need to identify the what is that. So first one, it is Ws actual and Ws ideal are what? Ws actual is the actual shaft work and Ws ideal is the ideal shaft work. So options, first one, it is Ws actual is greater than Ws ideal, and second one, Ws actual is less than Ws ideal. Option C, Ws actual is greater than or equal to Ws ideal. Option D, it is Ws actual is less than or equal to Ws ideal. So in actual stage, it should be Ws actual is greater than Ws ideal. Option A is the right answer, because as you can see that it cannot be equal, because in actual reasons given in the question itself, there are frictional pressure losses are there. So if losses are there, it cannot be equal the ideal conditions. So actual, it is always greater than, work done is more than the ideal shaft work when it is an actual operations. That actual operation is a two-stage compressor with frictional losses. So since losses are there, it cannot be equal. So in that case, it is greater than ideal, but it is not equal. So remember that it is greater than, it is not equal. So Ws actual is actually Ws ideal divided by eta. So efficiency is not always 100%. So it is will give more work, actually more work needs to be done. So that is one. These are the problems for week 5. Till now we have seen sample problems related to week 5, which will be helpful for you guys when you are solving the assignments for week 5 submission. Now let us look at some problems from week 4, for which assignment solutions have been posted in the website. So if you are interested in seeing how we are going to look at it anyway. So if you are interested in that, please check that. If not, it's your interest ultimately. But yeah, so that is one thing. Now we'll go to see week 4 assignment problems. First one, with increase of pressure at constant mass flow rate, overall volumetric heat transfer coefficient dash. Option A increases, option B decreases, option C remains constant, option D none of the above. So imagine with increase of the pressure at constant mass flow rate is constant, what happens to volumetric mass transfer coefficient? So it is P. It decreases actually. Option B is the right answer, because pressure is constant over here. Pressure is increasing, but mass flow rate is constant. So at that, if pressure is increasing, volumetric mass transfer coefficient, it decreases. Pressure, and that is inversely proportional, so it decreases. Option B is the right answer. Now go to question 2. In question 2, pressure drop in the riser of the fluidized bed may be developed on the basis of Option A, Bernoulli's equation. Option B, Newton's equation. Option C, Fick's equation. Option D, none of the above. So pressure drop in the riser of the fluidized bed is actually developed on the basis of Bernoulli's equations. So option A is the right answer. Now let us go to question 3. In question 3, pressure can change the bubble size in a fluidized bed. We all know that pressure changes the bubble size in the fluidized bed, and increase in pressure actually bubble size decreases, because with increase in pressure bubbles break, and because of that their size decreases. So answer is, with increase in pressure the bubble size dash. Option A increases, option B decreases, option C remains constant, option D none of the above. So the right answer is option D, decreases, because with increase in pressure the bubbles will be breaking, and because of that their size will be getting reduced, and also the formation will be uh, limited up to a certain smaller size. So that's why with increase in pressure the bubble size decreases. Option B is the right answer. Now let us go to question 4. In question 4, if you remember week 4, the problems are all related to frictional pressure drop inside the system. So problems will be related to that only. This one is just for giving you an idea and help. It might be helpful for your final exam. So final exams take into account some portion of the assignments and some portion of the final exam. So be careful in that. So pressure drop inside the bed may be due to option A, friction and acceleration of solids and gas. Option B, friction, head and acceleration of the solids and the gas. Option C, friction and heads of the solids and gas. Option D, none of the above. So pressure drop inside the bed, as you all know, it is due to friction, head and acceleration of solids as well as gas. Option B is the right answer. These things we have discussed enough in the last class itself, so that's why I am going in a hurry. If at any point of time you want me to stop, please let me know. Pressure drop inside the fluidized bed is equal to dp by dz total is equal to dp by dz head plus dp by dz acceleration plus dp by dz friction. So pressure drop inside the bed is due to friction, head and acceleration of the solids and the gas. Question 5. When the gas solid two-phase flow in a riser reaches a fully developed state, acceleration pressure drop dp by dz acceleration should be, these questions and all we have discussed in the last class itself. So if these were in assignment, it is very good actually. So is equal to 0 actually. So option A greater than 0, option B less than 0, option C equal to 0. Equal to 0 is the right answer. Option D none of the above. Answer is option C equal to 0. Question 6, it is about for low superficial gas velocities, particle diameters have almost no influence on the frictional pressure losses when the superficial gas velocities are. So we say that for lower superficial gas velocities, particle diameter have no influence on the frictional pressure loss. So when is that? So when it is less than 7 meter per second, greater than 7 meter per second, greater than 10 meter per second, greater than 12 meter per second. Option A is the right answer, less than 7 meter per second. That is with lower superficial gas velocities, particle diameters have no influence on pressure drop. So that particular lower superficial gas velocity is less than 7 meter per second is the right answer. So now moving go on to question 7. Oh, We'll see question 7. In question 7, it is asked that role of pressure drop in fluidization governs the pattern of energy dissipation, changes the fractional hold-up of the phase, changes the bubble size in a bubbling fluidized bed, all the above. This one also we have seen in last class itself. That role of pressure drop in fluidization, it governs the pattern of energy dissipation, and option B, it changes the frictional hold-up of phase, fractional hold-up of the phase, and changes the bubble size in a fluidized bed. All these are true, so answer is option D is the right answer. When we see question 8, it is under higher superficial gas velocities, the frictional pressure losses with Geldard's group A particles are greater than those with Geldard's group A particles. Group B particles are greater than group A particles. Geldard's group A particles are greater than those with Geldard's group B particles. Geldard's group A particles are equal to that with group B particles. None of the above. So I hope you all remember what is Geldard classification of solids. Geldard classified the solids into 4 classes: group A, group B, group C and group D. So this classification is based on relative density between the solids and the fluid and the size of the particles. So smallest particles comes under Geldard C, and comparatively larger particles comes under Geldard A, and sand-like sized particles comes under Geldard B, and further larger particles comes under Geldard D. So, at low superficial gas velocities, frictional pressure losses is independent of the particle size, but at a higher superficial gas velocities, say less greater than 10 meter per second, what is the frictional pressure loss relation between group B and group A particles of Geldard? So, group, it should be group B greater than group A, sorry, okay, group A greater than group B. With higher superficial gas velocities, frictional pressure losses with group A particles are greater than group B particles, because these particles are smaller. Okay, these particles are smaller than group B particles. So because of that reason, at a higher superficial gas velocities, the frictional pressure loss experienced by the smaller particles is greater than the larger particles. Smaller particles. This question actually comes in some other way, I remember. So we'll see if that comes. Smaller particles is greater than larger particles. Okay. Question 9. Pressure drop across the bed delta P at particulate regime is equal to the effective weight of the bed per unit area, greater than the effective weight of the bed per unit area, smaller than the effective weight of the bed per unit area, none of the above. So it is equal to the effective weight of the bed per unit area is the right answer. Option A is the right answer. I'll go to question 10. The accelerative pressure drop is the pressure drop due to acceleration of particles from inlet of the riser to the point where the particles attain maximum velocity, minimum velocity in the riser. Option B, maximum velocity in the riser. Option C, velocity equal to the inlet velocity in the riser. Option D, none of the above. Answer is actually maximum velocity in the riser. Option B is the right answer. Accelerative pressure drop is the pressure drop due to the acceleration of particles from the inlet of the riser to the point where they attain the maximum in the riser. So option B is the right answer. Question 11. The total frictional pressure drop is generated due to frictional force between gas and solid. Option B, frictional force between solid and the walls of the bed. Option C, frictional force between gas and the solids, gas and the wall of the bed. All of the above. Answer is all of the above, because the total frictional drop is due to the motion of the solids and the gas against each other and against themselves and against the walls. So frictional pressure drop force between the gas and the solid, gas and solid, and particles in the solid, particles in the wall, gas and solid is covered. So now gas and the wall and solid and the walls is also covered. So gas and particles, particles in the wall and gas in the wall. So all three factors should be covered. So answer is all the above. Option D is the right answer. Now we go to question 12. In question 12, frictional force per unit volume between the solid phase and the wall can be calculated by option A, Bernoulli's equation, option B, Fanning's equation, Option C, Dalton's equation. Option D, none of the above. Fanning's equation is the right answer. Frictional force per unit volume between the solid phase and the wall can be calculated by Fanning's equation. So this one also we have discussed enough in the last class, like those equations also we discussed if you remember. So you people must have been able to answer these questions rightly. Now let us go to question 13. In question 13, due to the lesser concentration of the solids in the riser, the friction between the gas and the solids may be negligible. Option B, solids and the walls of the bed may be negligible. Gas and wall of the riser may be negligible. All of the above. I think solids and the walls, or gas and solids. Option A or B should be. Okay, option A. Gas and the solids may be negligible. Yeah, because the concentration of the solids is less, so the friction between the gas and the solids would be negligible because solids are present in low quantity. Solids and the gas friction between them is less. So we are assuming they are negligible. Option A is the right answer. Question 14. With increase of solids concentration, even if the operating conditions have almost the same solids velocity, the frictional pressure losses dash. What are we doing? We are increasing the solids concentration. Even if the operating conditions have the same solids velocity, the frictional pressure losses actually it should increase. Option A decrease, option B increases, option C remains the same, option D none of the above. Answer is option B, increases, because as you have seen at lower concentration, the previous problem only we have seen, at lower concentration the frictional force between the gas and the solid is negligible, so we are neglecting that. So frictional pressure loss is less, but if we are increasing the solids concentration and even if you are operating at the same condition, the additional factors like between the gas and the solid now we have to consider, and it also cannot be negligible. So the frictional pressure loss on the whole is increased. So option B is the right answer. So if you put question 13 and question 14 together, you will be able to answer that. So that is question 14, and now it is question 15. Frictional pressure loss increases with increase of solid velocity and superficial gas velocity. Option B, increase of solid velocity and decrease of superficial gas velocity. Option C, decrease of solid velocity and increase of gas superficial velocity. Option D, none of the above. So when the velocity is increased for the solids as well as the gas superficial velocity, they will be constant movement against each other, and the frictional pressure loss would be more. The frictional force between the gas and the solids will be increased if the velocity of the solids and the gas superficial velocity is increased. So the increase of increase of solid velocity and the gas superficial velocity only will lead to increased frictional pressure loss. So our answer is option A. Option A is the right answer. Now let us go to question 16. In question 16, when the liquid velocity increases and gas velocity remains constant. So it is a three-phase bed. Remember that it is a three-phase bed. And so we are assuming when liquid velocity increases and gas velocity remains constant, epsilon L by epsilon GL. So epsilon L increases, so the ratio on the whole increases, and so rho GL increases. Thus, in contrast with two-phase fluidized bed, del P Fr by L decreases, del P Fr by L increases, del P Fr by L remains constant, none of the above. This value remains a constant in case of two-phase fluidized bed. In two-phase fluidized bed, if liquid velocity is increased after the fluidization phase, the pressure drop, frictional pressure loss remains a constant. But in three-phase fluidized bed, with the increase in velocity of liquid And keeping the gas velocity constant, what happens is that delta P Fr by L decreases. The pressure loss decreases when we are increasing the liquid velocity and keeping the gas velocity constant. Why? Because liquid fraction increases and density of the gas, GL increases. So compared to two-phase fluidized bed, it changes here, and also it changes in a specific manner as it decreases. Delta P Fr by L decreases. So option A is the right answer. Question 17. Let us go to question 17. Okay, it is a problem. In question 17, it is asked that air whose density is 1.22 kg per meter cube and dynamic viscosity is 1.9 into 10 power minus 5 pascal second is flowing in a fixed bed of diameter 0.5 meter and height 2.5 meter. Bed is packed with spherical particles of diameter 10 mm. Void fraction is 0.38. Air mass flow rate is 0.5 kg per second. Calculate the pressure drop across the bed of particles. So answer is, options are 0.276 into 10 power 5 pascal, 0.286 into 10 power 5 pascal, 0.294 into 10 power 5 pascal, and option D 0.264 into 10 power 5 pascal. So air we are passing inside the fluidized bed or fixed bed whose dimensions are diameter 0.5 meter and height 2.5 meter, and the bed is packed with solid particles whose size is 10 mm and the void fraction is 0.38 and the air flow rate is 0.5 kg per second. So the density and dynamic viscosity are 1.22 kg per meter cube and 1.9 into 10 power minus 5 pascal second for air. So answer is actually 0.264 into 10 power 5 pascal. So we look at the answer solution method. Given things are air, its density and dynamic viscosity and mass flow rate is 0.5 kg per second. And fixed bed whose bed dimensions are diameter and height is given, and particles spherical, so sphericity is 1 and diameter is 10 mm and void fraction of the bed is 0.38. Now we need to find pressure drop across the bed, and for that we need to find we need to do the calculation. So for that we are using the Ergun's equation. Delta P by L is equal to 150 V mu 1 minus epsilon square by 5 into dP the whole square epsilon cube plus 1.75 rho V square into 1 minus epsilon divided by 5 dP epsilon cube. So first we need to find the Reynolds number. Reynolds number is rho V dP by mu. So V is superficial gas velocity and here we are given the mass flow rate. So mass flow rate divided by the density would give us volumetric flow rate, and volumetric flow rate divided by the area of the cross-sectional area of the column will give us the superficial gas velocity of the gas. So for that purpose it is mass flow rate divided by density divided by the area of the column. So area of the column is pi r square, that is cross-sectional area of the column. So it is 0.5 divided by 1.22 divided by 3.14 into 0.25, that is 0.5 divided by 2 the whole square is equal to 2.08 meter per second. So and we are substituting in the Reynolds number formula rho V dP by mu. So rho is 1.22, V is 2.08, dP is 10 mm, 10 into 10 power minus 3, so it is 0.01 divided by 1.9 into 10 power minus 5. So we are getting value as 1335.58, which is in turbulent regime. So it is sufficient if we take this factor alone into consideration. Delta P by L is equal to 1.75 rho V square into 1 minus epsilon divided by 5 dP into epsilon cube. So we have substituted all the values and we are getting the value as 26,091 pascal, which is nothing but 0.261 into 10 power 5 pascal. Oh, and the value given is 0.264 into 10 power 5 pascal. So answer is option D is the right answer. I hope now it is clear. I mean, simple problem similar to that we have seen in the last class also. So I am moving to next problem. Question 18. In question 18, when Reynolds number REF is less than 2300, fluid friction factor is calculated using empirical Blasius formula as dash. So this one we have seen last class itself. If Reynolds number is less than 2300, fluid friction factor is 24 by RE, because is less than 2300. We know that fluid Reynolds number. So similar to that, particle Reynolds number is less than 2000. I mean less than 1. I mean less than 0.1. I remember some very low values. It is 24 by REP. Similar to that, Blasius formula is using fluid Reynolds number here. There it is particle Reynolds number, which we use for calculating drag coefficients. It is equal to 24 by REP. If Reynolds number is low, that is in the Stokes regime. But if fluid Reynolds number REF is less than 2300, fluid friction factor is calculated using Blasius formula. And what is that? So this problem also we have seen in the last class. So I think this week's assignment should have been very much easier for you guys if you had followed the session. Even without that, it was easy. Like everything was covered from the theory, and two more problems were there. I saw them being from the course, so I haven't put it here because sir himself has given the solution for those. So I haven't included those problems. And option E, it is FF is equal to 16 by REF. Option B, FF is equal to 24 by REF. Option C, FF is equal to 36 by REF. Option D, FF is equal to 18 by REF. So option B is the right answer, 24 by REF. So similar to that drag coefficient formula, here we are calculating the fluid friction factor when given the Reynolds number. What Reynolds number? Fluid Reynolds number. So 24 by REF is the right answer. So that is for problems. Two problems I have included because they are same from the sir's course. So that I have eliminated. And one more thing is, last week's problem, I was taking, no, like this is from week 2 assignment problem, and I have put it in week 3 as well and last week's as well. Week 3 I gave one method, and in last week I was giving one more method, but there was some calculation issues in the last week, so I told I would be giving in next class. So that one I have included in today's class actually. Like last week we have given the formula, there was some substitution and unit confusion mainly, so which I have found out actually, and I am giving it in today's class. So the problem is, calculate the terminal velocity for the sharp irregular sand particles whose density by using gas in gas medium. Density of gas is 1.2 into 10 power minus 3 gram per centimeter cube, and viscosity is 1.8 into 10 power minus 4 gram per centimeter second. dP is 160 micrometer, and density of solid is 2.6 gram per centimeter cube, and 5s is 0.67. So it is sharp irregular sand particles, and we are supposed to calculate this terminal velocity. So options given are 88 centimeter per second, 66 centimeter per second, 77 centimeter per second, 55 centimeter per second. So answer is actually option A, 88 centimeter per second. So we will look at the solution. First one, we are writing the given. Please write given formula calculation so that it would be easier for you also to solve, to know what is given and to know where to implement the given things exactly. And if it is a theory exam in your college, it will actually be helpful for the correcting faculty to be identifying everything that is needed. It would not, you would not be giving space to get the marks reduced. So it would be added advantage, and it would be giving that you are having a very clear idea of what you are doing. That image it will give. So just a suggestion. So first we are writing given. Given it is density of gas is 1.2 kg per meter cube. I have put all the units in the unit convenient for me, that is SI unit. I have just changed the unit, and viscosity of the gas is 1.8 into 10 power minus 5 kg per meter second, and the diameter of the particle is 160 micrometer, and density of solids is 2600 kg per meter cube. and 5 years is 0.67. Now we are supposed to find UT. And how are we going to find UT? We need some formula. Formula is, first we need to find dimensionless diameter, and using that dimensionless diameter we need to find dimensionless terminal velocity, and after that we need to find the original terminal velocity. So that is the case. So this formula is applicable in the range of 0.5 to 1 sphericity. Our sphericity is 0.67, so we can use it. So first we are using dp star formula, and dp we are substituting, and rho g is 1.2, rho s is 2600 minus rho g 1.2 into 9.81 divided by 1.8 into 10 power minus 5 the whole square. I have put it as 1.8 square into 10 power minus 10 and to the whole power of 1 by 3. So that gives us 7.28. Now we are using this dp star in ut star equation. Ut star is equal to 18 by 7.28 the whole 7.28 square plus 2.335 minus 1.744 into 5 years. 5 years is 0.67 divided by 7.28 the whole power of 0.5 whole to the power of minus 1. So again we are getting 1.2953, and now we are using this ut star in here and getting the ut value. Ut star is equal to u star divided by the whole thing, right? So ut is equal to ut star divided by rho g square, that is 1.2 square, divided by 1.8 into 10 power minus 5 into 2600 minus 1.2, that is rho s minus rho g into g and whole power of 1 by 3. So on substituting we are getting the value as 0.884. What you will be getting is 0.8847 meter per second, which is nothing but 88.47 centimeter per second, right? 88.47 centimeter per second, and which is nothing but 88 centimeter second. So if you go back and look at the option, it is 88 centimeter per second. That is option A is the right answer. So in last week itself we have seen the problems. Only one issue was there, that is I did some mistakes while substituting the values. So rest other things like formula was right, just some substitution error was there, so which I have rectified in today's class. So answer is 88 centimeter per second. So that's it for today's class. Thank you guys for attending. If you have any doubts you can ask, and if you have any feedbacks for me, that also we can discuss. If you have any doubts, please let me know. In today's class we have seen the problems about week 5, wherein we were dealing with gas distribution system problems, and also we have seen the solution to the last week's assignments. I mean we just discussed the week 4 assignment problems, for which the answers were released last week Wednesday. Last week Wednesday was the final submission date. So we have seen the problems. I mean we in this class we discussed the answers given in that class as well, and the week 5 sample problems also we have discussed. So these sample problems will be helpful when you are solving the assignments. So that is one thing. Please submit the assignments on time if you are planning to write the final exams, because it will be bonus and you will be getting some I mean you will be getting marks, which is very important if we are giving the final exams, because final exams mark includes the marks from the assignments as well. So that is one thing. It is some proportion of marks from assignments will be included, and if you are planning to take some future in fluidization, you should be very learn everything properly, because it is an interesting aspects and it has large potential actually in industry as well as academia. Yeah, that is there. So yeah, we have seen today's class. I'll wait for 5 more minutes. If you have any doubts, you can ask, or else we can close the session. I'll wait. If you have any doubts, we can discuss, or else please close. So yeah, we'll see. I guess everyone left, so we'll also close the session. Yeah, thank you for attending the sessions, whoever has attended. So we'll meet again next Saturday from 3 p.m. to 5 p.m. unless otherwise informed of some other changes. So thank you guys. Thank you.